Welcome back to Weapon Science. I'm Ethan Walker. Imagine a machine the size of a 10-story building beating at just 80 revolutions per minute. This slow-moving mechanical heart drives a 300,000-ton vessel across the world's roughest oceans. How is this possible? Theoretically, nuclear energy is the perfect power source. High energy density, near-zero carbon emissions, and years of operation without refueling. Yet, in the harsh, pragmatic world of maritime commerce, this perfect energy is avoided like a plague. Many demand that giant merchant ships adopt nuclear reactors to curb global pollution. But marine engineers and naval architects shake their heads. Why do these experts reject such an elegant, environmentally friendly solution? Look at the Nimitz-class aircraft carrier. It uses nuclear propulsion to sail for 2 decades without refueling. It's a feat of military engineering, providing limitless range and operational dominance for a superpower. If it's so great, why don't very large crude carriers or massive container ships use it? They sail global routes 24/7. Surely the range would be a massive financial gain, but the industry sticks to 2-stroke diesel engines. Today on Weapon Science, we dissect these ocean giants. We'll dive into the harsh realities of marine engineering, analyzing hydrodynamics, and the invisible clash between physics and global economics. To understand the present, we look back to 1959. The NS Savannah was the world's first nuclear-powered merchant ship. It was a futuristic beauty, a symbol of peaceful atom use, and a technological marvel. Technically, it worked flawlessly. Commercially, it was a disaster. The first issue? Radiation shielding. To protect the crew, the reactor needed thousands of tons of lead, concrete, and thick steel. In logistics, space is money. Every cubic meter spent on concrete shielding is a meter that cannot carry cargo. The Savannah's cargo capacity was dismal compared to conventional ships of the same size. Then there's the crew. You can't just hire a regular mechanic for a nuclear reactor. You need highly qualified nuclear engineers whose salaries and rigorous safety training costs choke thin profit margins. The Savannah taught us a bitter lesson. Exotic, high-density energy doesn't always align with economic efficiency. Commercial ships don't need lightning speed. They need the lowest cost per ton of cargo. Let's look at thermodynamics. Converting raw heat into mechanical movement for a slow, high-torque ship is incredibly inefficient. A nuclear reactor is essentially an expensive giant water heater. Steam turbines spin at thousands of RPM, but ship propellers need to spin under 100 revolutions per minute to avoid cavitation. This requires massive heavy reduction gears that sap even more energy through friction. The steam system needs massive cooling, complex piping, and high-pressure valves, a nightmare for reliability. Compare this to the brutal simplicity of a 2-stroke diesel engine. Modern marine diesels are engineering masterpieces. No turbines, no reduction gears. The engine is directly connected to the propeller shaft. If the engine hits 80 revolutions per minute, the propeller hits 80 revolutions per minute. To get enough torque without gears, these engines are massive. Cylinders are nearly a meter wide, and piston strokes are 3 meters long. Every cycle produces huge force, converted into pure rotational torque. 2-stroke cycles mean a power stroke every turn of the crank. This provides constant, smooth torque. No wasted intake or exhaust strokes, just pure, relentless mechanical power. These engines hold the record for the most efficient internal combustion engines on Earth, with thermal efficiency exceeding 50%. Most of the energy goes into movement, not just wasted heat. Even that remaining heat isn't wasted. Exhaust gas boilers capture it to heat fuel, create fresh water via desalination, and power generators. It's a closed loop of extreme efficiency. This is the iron law of maritime thermodynamics. Direct efficiency and mechanical simplicity always beat exotic complexity. Nuclear energy is dense, but the conversion process is simply too inefficient for commerce. Why stick with fossil fuels? Enter bunker C, a thick, sludge-like residue from oil refining. It's the cheapest fuel on Earth, the literal dregs of the barrel, and it keeps global trade moving. In a business where fuel costs are half of the operational budget, this cheap, dirty sludge is an economic necessity. It's the black blood of international commerce. Burning this asphalt-like fuel requires skill. It must be heated to 130 degrees Celsius to be pumpable. Once it hits the atomized cylinder, it explodes with immense power. Nuclear fuel is cheap. But building a certified maritime reactor costs billions. Over a 2-5 year ship lifespan, the cost of oil is still vastly cheaper than the capital, insurance, and security costs of nuclear. Then there's the not in my backyard syndrome. Would Singapore or Shanghai allow a nuclear reactor in their ports? The political risk of a potential radiation leak is a non-starter for any city leader. The NS Savannah spent most of its life anchored offshore because ports refuse to let it dock. A cargo ship that can't enter a port is just a floating paperweight. It's a logistical paradox. Diesel ships can be repaired anywhere. Spare parts are global. Nuclear reactors require specialized, military-grade facilities. If a reactor breaks in the middle of the ocean, the ship is stranded. And what about security? Shipping uranium-powered vessels through pirate-prone zones like the Gulf of Aden without a military escort is a massive safety risk. It's an easy target for terrorism, so we stick to oil. But we fight for efficiency elsewhere. Enter the dark arts of fluid dynamics. Water is 800 times denser than air. Moving a massive hull is a constant battle against friction. Look at the bulbous bow. That nose-like protrusion below the waterline isn't for show. It creates a secondary wave that cancels out the bow wave of the ship, reducing drag by 15%. Skin friction is the other enemy. Millions of square meters of steel dragging through water. We use specialized paint to keep it smooth, but we need something more radical. Air lubrication systems pump micro bubbles under the hull. The ship literally glides on a carpet of air, cutting friction and saving another 5 to 10% in fuel. It's pure physics at work. The propeller is the final interface. Massive bronze blades, over 10 meters wide. Why so big? To push a huge mass of water slowly, rather than a small mass quickly. Accelerating a small mass of water creates turbulence and waste. A large, slow-turning propeller captures a massive column of water, pushing it back with far greater efficiency. But watch out for cavitation. If the blades spin too fast, local pressure drops, and water boils cold, creating bubbles that implode and eat away the metal like acid. Engineers use computational fluid dynamics to sculpt these blades. Every curve is designed to delay cavitation while maximizing thrust. It's a delicate, high-stakes dance with nature. Devices like the Mewis duct straighten the water flow before it hits the propeller, further increasing efficiency. Every bit of design is about squeezing performance from every drop of fuel. But the game is changing. Climate change is forcing the industry to zero emissions. The IMO's regulations are an existential threat to bunker fuel. Wind is back, but not with sails. Rotor flattener cylinders use the Magnus effect to turn crosswinds into forward thrust, assisting the main engine and saving fuel. Liquid natural gas is the first step. But the ultimate goal? Green ammonia and liquid hydrogen. Fuels that can be burnt or used in fuel cells to release zero carbon. Hydrogen requires cryogenic storage at minus 253 degrees Celsius. Ammonia is toxic. The engineering challenges are massive, but the race is on to solve them. Nuclear won't be the answer for commerce. The future is giant, slow-moving ships powered by clean synthetic fuels. Mechanical simplicity will remain king of the seas. The story of the VLCC rejecting nuclear power is a lesson in applied pragmatism. Engineering isn't just about what's possible. It's about what works in the real world. Every product you own was brought to you by these invisible giants. They are the backbone of modernity, working tirelessly in the dark to connect our world. Next time you see a container ship, don't just see steel. Imagine the ecosystem of fluid dynamics, the massive pistons, and the precise engineering holding it all together. It's a symphony of 20th century mechanics preparing for the 21st century ecological transformation. We aren't just moving cargo. We are manipulating the laws of nature. Nuclear will stay in the military, where cost is secondary to dominance, but for the rest of us, the slow, steady hum of commerce will continue on its own terms. As we move forward, we might see rotor sails or clean ammonia exhaust, but the core principles of efficiency and safety will never be compromised. That is the way of the sea. Engineering is full of brutal compromises. Understanding these trade-offs is how we build a better world. I hope this perspective has changed how you look at the ocean. If you enjoyed this deep dive into marine engineering, hit subscribe. Join our community of rational thinkers as we explore the wonders of the man-made universe. What do you think? Will small modular reactors ever find their way onto commercial ships? Or will green hydrogen win the race? Let's discuss in the comments below. Your likes help our algorithm spread this science-based content to those who thirst for knowledge. It keeps our team motivated to continue our work. Know an engineering student or a logistics professional? Share this video with them. Spreading knowledge is our mission here at Weapon Science. Thank you for joining me in the depths of marine engineering and economic physics today. Check our playlist for more documentaries on megastructures. I'm Ethan Walker. Stay critical, stay curious, and see you in the next scientific adventure. This is Weapon Science, signing off. Let's dig deeper into the metallurgy of those propellers. High-strength bronze is essential to withstand the intense pressure of cavitation while maintaining structural integrity. The alloys are carefully chosen. Nickel aluminum bronze is the standard, offering superior resistance to seawater corrosion and the mechanical stress of constant propulsion. Corrosion is another silent killer. Sacrificial anodes are placed across the hull to protect the steel, slowly eroding so the ship doesn't have to. Stability is crucial for these massive tankers. Ballast water tanks are constantly adjusted to keep the ship upright even during violent storms. Modern navigation uses satellite data to optimize routes, avoiding bad weather and currents to save fuel. Its efficiency at a planetary scale. Engine rooms are now highly automated. Sensors monitor temperature, vibration, and pressure in real time, allowing for predictive maintenance before a failure occurs. The supply chain is a delicate balance. A delay in one port can ripple through the global economy. This is why reliability is valued over everything else. Despite all the tech, the human element remains vital. Skilled mariners navigate these massive machines, ensuring safety and efficiency in unpredictable conditions. Safety protocols on tankers are incredibly strict. Double hulls are mandatory to prevent oil spills in case of collisions or groundings. We are reducing the environmental footprint. From scrubbers to low-sulfur fuel, the industry is moving toward a cleaner future, even if it's slow. International regulations are the driving force of innovation. They set the bar that all companies must meet to keep operating. Without these ships, global trade would collapse. The economy depends on this dirty but efficient engine to function. Scale is the true challenge of engineering. Keeping a machine this big efficient is a feat that deserves more respect than it gets. We are on the verge of a revolution. AI-driven ship design will optimize hulls and propellers even further, pushing the limits of what's possible. We must rethink energy density. How can we pack more energy into smaller, safer, and cleaner volumes? That is the next great engineering hurdle. We choose the path of least resistance, but science allows us to push boundaries. Every innovation is a step toward a better tomorrow. Progress is rarely a straight line. It's a series of compromises, failures, and breakthroughs. This is the nature of the scientific journey. Reflecting on these giants, we see our own ambition. We build to connect, to provide, and to survive no matter the cost. Our legacy will be the structures we leave behind. These ships are the machines that built the modern world. Nature has rules, and we learn to work with them. Physics is the ultimate arbitrator of what can and cannot be done. I hope you have learned to appreciate the complexity hidden in plain sight. It's a fascinating world. If you know where to look, don't forget to check our links in the description for more technical resources. Keep exploring, keep questioning, and keep learning. Join us next week as we explore the hidden science of skyscrapers. You won't want to miss that one. This is Weapon Science, where we simplify the complex. See you next time. Stay curious. Ethan Walker, out.